Solving problems for exponential growth and decay. Here's the basic exponential formula to use. The final amount equals the initial amount times the growth or decay rate to the exponent, time divided by period. But what does this mean? The final amount is the amount that you're left with at the end of the time that you're measuring over. The initial amount is how much you have available at the beginning of the time period that you're measuring. The growth rate is how much the amount that will be growing over each period. It will double, it will triple, it will go by 3%, it will decay by 1/2. Those are examples of growth rates. The decay rate is the 1/2 that I've already talked about, which is how much it will decay or decrease each period. So half means it decays by half its value each period. Time is the total length of time that you're measuring over. 10 years, 20 years, other values. Period is the length of time it takes for one period or one cycle. So it doubles every 3 years. So your period would be 3 years. Here's an example. A bacterial culture began with 7,500 bacteria. Its growth can be modeled using the formula N equals 7,500 times 2 to the exponent T divided by 36, where N is the number of bacteria after T hours. So N would represent our final amount. We want to know how many bacteria are present after 36 hours. Then, how many bacteria are present after 72 hours? How does this relate to the doubling time? Now, we know that N, we said, was the final amount, the number left at the end of the time. The initial amount is what we start with. We're starting with 7,500 bacteria. The growth rate is 2. Now, 2 happens to mean doubling. So this is doubling every period. So that's how many bacteria will grow in the time of one period. The decay rate, since the rate is greater than 1, this is not a decay, but it's a growth. Time is the amount of time that we are measuring over. Now we're using the variable t to represent time. The period is 36. This means that the number of bacteria will double every 36 hours. So that's the length of time it takes for one cycle. Now that we've analyzed, let's identify what we are trying to find. Now we wanted to know how many bacteria there were after 36 hours. So how will we do that? We will substitute T for 36 into the equation. So we will know that the total number, the final amount, if you will, is equal to 7,500 times 2 to the exponent 36 divided by 36. Now, we all know that 36 divided by 36 is 1, so it simply becomes 7,500 times 2, which is 15,000. Now, if we look at the relationship between 7,500 and 15,000, it has in fact doubled. So our conclusion, there are 15,000 bacteria present after 36 hours. Now, part B to this was after 72 hours. Substitute in the equation. This time the value of T is given as 72 hours. So when we work this out, we'll solve N, the total number that is at the end of the growth cycle we're measuring over, the growth time frame. So 7,500 times 72 over 36 simplifies to 7,500 times 2 to the exponent 2, which is 30,000. So after 72 hours, there are 30,000 bacteria present. Here is another example. All living organisms contain a known concentration of 1 part per trillion parts of carbon-14. Now, carbon-14 happens to be a radioactive element, and it is very useful in dating ancient artifacts because its half-life is about 5,330 years after the organism dies, which is a very long time. So what's our formula? Well, we want to find out how much carbon exists after a certain period of time. So this is a decay question because our value is half-life. We want to know over how many time, so N, and one half-life, one cycle, one period is 5,730. So if we found some cloth and we think that it's 5,730 years old, we're not sure, but we think, because we weren't around then, you know, what would be the carbon concentration of carbon-14 in this piece of cloth, which happened to have been made from plant fibers, by the way, after 5,730 years? Now, let's say we measured an animal bone, perhaps a dinosaur. What would be the concentration of carbon-14 in this animal bone after 50,000 years? Round your answer to 5 decimal places. Interesting. So we'll take the first one. So C is our final amount. Our initial amount is 1 because we weren't given that value, so indirectly we know it's 1. The growth rate is less than 1, greater than 0, so this is decay. So the decay rate is 1/2. T is time, Given in the question, the length of time over which the problem is for, and it's represented by n, and the period is 5,730, the length of one half-life. So, part A, for C, what are we trying to find? N is 5,730 years. Substitute into the equation, so 1 times 1/2 to the exponent, 5,730, divide by 5,730, we solve, and we get 0.5. So after 5,730 years, the concentration of carbon-14 would be from 1 to 0.5 parts per trillion. That's a very small amount. Here's part B. In this one, we're trying to find the bone after 50,000 years. Substitute into the equation. C is 1 times 1/2, 50,000 divided by 5,730. Use your calculator and you will find that C is 0.00236. So after 50,000 years, the concentration of carbon-14 would be 0.00236 parts per trillion. Now that we basically understand how the exponential function works for growth and decay, let's start the next part of our lesson.